Hello again, and welcome to the first of two lectures on counting principles and elementary probability. Today we'll talk about permutations and combinations, and then in the next lecture we'll apply these ideas to some probability questions. We'll talk about things like how many different telephone numbers are possible, or how many different lottery tickets are possible. How many ways can you form a team of players? How many poker hands are possible? How many ways can you roll the number 7, say, with 2 dice? These are neat questions. This is fun stuff, I think, because it has a lot of everyday appeal. These are questions that we often ask ourselves. And that said, it's also a big subject at universities. In our department, we teach many courses on probability, and over in the statistics department, they have many more courses on probability. These ideas are, at one level, fairly straightforward, as we'll see in our lectures, but higher level probability is based on calculus, actually, so it's a very deep topic. All right, let me start with, again, as I usually do, with some fairly simple examples just to get us warmed up about counting principles. Suppose the following is going on. I've got a box here with 8 numbers in it on pieces of paper. So the pieces of paper have the numbers 1 through 8 on them. One paper has a 1 on it, the other piece has a 2, etc. So there are 8 pieces of paper. And I reach into the box and pick out a piece. And then I write down the number that I picked out. Then I put that piece of paper back into the box, shake it up again, and reach down again and pick out another number and write it down. Okay, so I've done this twice now. So here's the question. If I add up those 2 numbers to get a final number, in how many ways can a sum of 12 be obtained? Okay, you pick a number, write it down, put the number back in the box. Shake it up, pick another number, write it down, add them up. In how many ways can a sum of 12 be obtained? Well, let's count the ways. If the first number's 4 and the second number were an 8, I'd get 12. If the first number were 5 and the second number were 7, again, I'd get 12. I could have picked a 6 out in the beginning, and because I put it back in the box, it's still there, and I might have picked it again. So that's another way of getting 12. I could have picked a 7 and then a 5 and an 8 and then a 4. And there are no other ways, are there? If you had picked a 3, you're doomed. It's too small. Or if you'd picked a 9, again, you're doomed. So there are 5 ways of obtaining the sum of 12. Let's twist the problem slightly. The only change now is I reach into the box, pull out a number, write it down, but I don't put that piece of paper back in the box. Okay, it's not back in the box. So then I reach in again and write the second number down. How many ways can I obtain a 12 now? Well, let's count them again. I could have picked a 4 the first time and an 8 the second time, a 5 the first time and a 7, but now that 6 won't work, will it? Because I need to have the 6 back in the box, and I've taken the 6 out and I'm not putting it back in the box. So that way is gone. And then, of course, a 7 and a 5 and an 8 and a 4. So now there are 4 different ways. Okay, that was a pretty simple problem because we were able to actually list all the possible outcomes and just count them up. 5 in the first example, 4 in the second example. This is not feasible for more complicated problems. So we're going to have to develop some tools for handling more complicated counting problems. One of the tools we'll use is the fundamental counting principle. Here's how it goes in technical language, and then of course I'll illustrate it with some examples. Suppose you have 2 events, call them E1 and E2. And the first event, E1, can occur M1 different ways, and the second event, E2, can occur M2 different ways. So, and in this way, what I mean is that after E1 has occurred, then E2 independently can occur in M2 different ways. So how many ways can the 2 events occur? And that's the product, M1 times M2. Let me illustrate that principle with a very simple example. How many different pairs of letters from the English alphabet are possible? How many different pairs? Okay, well, there are two events in this situation. The first event is the choice of the first letter, and the second event is the choice of the second letter. And they're independent of each other. So I pick the first event has 26 possibilities because the alphabet has 26 letters. And so it's 26 times 26, or 676 possible pairs of letters. See how that works? 26 is the first event. I can pick one of 26, and then the second event, and you multiply them together. Let's do a slightly harder problem. Telephone numbers. In the United States, telephone numbers have 10 digits. As you know, they have an area code for 3 digits and then a 7-digit number. So here's my question for you. Within a given local area code, how many different local numbers are possible? How many different 7-digit numbers are possible? So imagine you're in my Florida area code, 352. How many different 7-digit numbers are possible in that area code? And we're going to assume that 0 or 1 cannot be the first digit in the telephone number. Okay, let's count how many possible telephone numbers there are. And it's this same counting principle. Here we go. The first digit of a telephone number, it can't be a 0 or a 1, so it has to be 2, 3, 4, or possibly out to 9. It can be one of 8 different choices. We have 8 choices for the first number, 2 through 9. For the other 6 digits of our telephone number, we have 10 choices, don't we? 0 through 9. So the total would be the product of these 7 numbers, 8 times 10 to the 6th power. 10 times 10 times 10 times 10 times 10 times 10, 6 times. That's a big number. 8 times 10 to the 6 is 8 million. There are 8 million possible telephone numbers within that single area code. Now, that seems like a big number, of course. Speaking practically, is it really such a big number in today's world? In my household, we have a landline, and we have a couple of cell phone numbers, and we have a fax number. That's already 4 telephone numbers in one home. So you can imagine that this number, 8 million, is not very big after all. And I think around the country you see all the time where certain area codes are split into 2 pieces and dividing up because they've run out of telephone numbers. This happens all the time. So despite this large 8 million number in today's world with cell phones and faxes and things, it's actually not that big. All right. Let's turn to the first of the 2 topics I'd like to study in more depth, permutations, and then we'll go later on to combinations. So here's what I mean when I say permutations. This is the number of ways that you can arrange n objects, n elements in order. For instance, let me give you an idea. Suppose you have 8 people. And you'd like to arrange them in a line with a first person here and then a second person and a third person like that. So it's 8 people and they're in a certain order. It's a different order if I'm in front than if I'm second in line. Those are different orders. So the order is important here. A permutation of n different elements is a ordering of those elements such that one element is first and another one is second and another one is third. It's not like, say, forming a basketball team. 5 players make up a basketball team, but there's no order involved there necessarily. You just have the 5 players. So we're talking about an ordering of objects. Let me show you some examples, a very simple example. In how many ways can we order 4 people so that they stand in line, a first person, a second person, a third person, and a fourth person? Well, let's count the ways here. There are 4 possibilities. We have 4 people. So there's 4 possibilities for that first position. And once you fill that first position, there are just 3 people left for the second position. So there are 3 possibilities. Then there are 2 possibilities for the third position, and then the last person is stuck at the end of the line. So it's a multiplication problem by that basic principle, 4 times 3 times 2 times 1. Do you recognize that number? 4 times 3 times 2 times 1? Right, that's 4 factorial, isn't it? Remember that notation we introduced, 4 with an exclamation point after it? 4 factorial, or n factorial, means n times n minus 1 times n minus 2, all the way down to 3, 2, 1. So this factorial notation will play a big role in permutations and later in combinations. So here's the theorem. The total number of permutations of n elements, n objects, n people, is given by n factorial. N times n minus 1 all the way down to 1. So it's n factorial is the answer here. All right, let's complicate things slightly. We go to horse racing. And in horse racing, it's often very important to know who wins and who comes in second and who comes in third. Those are the ones that usually get prizes. So here's the setup. Suppose you have 8 horses running in a race. In how many ways can these horses come out in the following position? There's a first horse, a second horse, and a third horse, and I don't care about the rest of them. So how many ways can they come in first, second, and third? Okay, let's figure it out. How many choices are there for the winner? Well, there are 8 horses. We're assuming they're equally likely to win. So there are 8 possibilities for the winner. And then how about second place? Well, now there are only 7 horses to choose from, so there's 7 choices for second place, and I think you see the picture, there are 6 choices for third place. So the answer would be 8 times 7 times 6, or 336 different ways we can order these horses so that 3 of them come in first, second, and third. Now, this is a type of permutation slightly more complicated than the first example we did. It's called a permutation of n elements taken r at a time. We had 8 horses taken 3 at a time. That's how you would say it. 8 horses taken 3 at a time. And there's a formula for calculating such situations. Let me show you the formula, and we'll talk about it for a minute. It's kind of a funny notation in the literature. It's a capital P with a couple of subscripts. In the front, there's an N, and after the P, there's a subscript R. So why don't we call it NPR? And that means the permutation of n elements taken r at a time. In the example we just did, the notation would be 8P3. N was 8. There were 8 horses, and we took them r times, 3 at a time. So it's NPR, and here's the formula for that computation. And it uses our factorial friends. The numerator's n factorial, the denominator is n minus r, all factorial. So it's n factorial over n minus r factorial. Let's check that formula with the example we just did with the horses. Okay, so it's 8P3, so the numerator's 8 factorial, that's what n is, 8 factorial in the numerator. The denominator would be n minus r, 8 minus 3 factorial. In other words, 5 factorial. Now, 8 factorial over 5 factorial. A couple of ways of evaluating that. One way would be calculate 8 factorial. Not so pleasant. It's a big, long string of numbers. And then calculate 5 factorial, then divide them. Let me show you a shortcut. 8 factorial means 8 times 7 times 6 times 5 times 4 down to 1. Let me tell you what it means in a different language. 8 times 7 times 6 times 5 factorial. Because 5 factorial is the rest of the string, isn't it? 5, 4, 3, 2, 1. So you can write 8 factorial as the following. 8 times 7 times 6 times 5 factorial. And look at the denominator. It's also 5 factorial. Cancel them. And I'm left with 8 times 7 times 6. Oh, that looks familiar. That's what we just did with the horses. 336. So you see that little trick? We'll play with that trick in a moment. But let me first mention this funny symbol NPR. And this formula is, fortunately, like so much of pre-calculus, it's built into your calculator as well. Isn't that nice? So if you have a really big problem with giant factorials, you can use your calculator and that special button to figure out the answer. All right. I mentioned about this factorial trick, how we cancel that 5 factorial. Let's make sure we're comfortable with this cancellation trick. Let's simplify a couple of factorial expressions. How about 10 factorial divided by 8 factorial? All right, here would be the slow way. Calculate 10 factorial. All right, yuck. Calculate 8 factorial. Yuck, and divide them. Here's the clever way. 10 factorial is 10 times 9 times 8 factorial, isn't it? Because 8 factorial is 87654, so the whole string is 10 factorial. And now cancel the 8 factorials in the numerator and denominator. You're left with just 10 times 9 or 90. Isn't that cool? How you don't have to get your hands so dirty when you calculate that. It's some clever cancellation. Here's another one. 10 factorial over 8 factorial times 2 factorial. All right, I think you see how to do it. 10 times 9 times 8 factorial in the numerator. Denominator is 8 factorial times 2 factorial. Cancel the 8 factorials, and you're left with 10 times 9 divided by 2. 2 factorial is 2, and that's 45. Okay? So, and in the workbook, you'll have a few other examples of this simplification to play with. It's a nice trick. You avoid some unpleasant factorial calculations. Let's move on to baseball. We did a problem earlier with baseball having whether or not a certain batted ball was going to be a home run. Here's a completely different baseball application. Suppose you're a manager of a baseball team and you've got 13 players who are in the field, who can be batters, and you want to choose a batting lineup of 9 players. You want somebody to bat first, somebody to bat second, down to somebody to bat ninth. So as manager, how many different batting orders are possible using your 13 players? How many different batting orders are possible? Well, this is a permutation of 13 elements taken 9 at a time. So our symbol will be 13p9. And the formula says that's 13 factorial divided by 13 minus 9, n minus r. So it's 13 minus 9 factorial. So we have to compute 13 factorial divided by 4 factorial. Well, this is, even our fancy simplification techniques don't really work that well here. This is a little ugly. But here we go. 13 factorial is a giant string, isn't it? 13 times 12 times 11, all the way down to 6, 5, and then 4 factorial. And I stop at 4 factorial because that's what the denominator is. So I can cancel the 4 factorials. Slightly simpler. And now I'm left with this giant multiplication. 13 times 12 times 11, all the way down to 7, 6, 5. Trust me, here's what you get. 259 million. It's even bigger than I thought. 459,200. That's a lot of different batting orders. Maybe that's why managers are paid so much money. They have to work out which is the best batting order given all these possibilities. Okay, let's pause for a minute and talk about what we've been doing. Notice something obvious. It would have been much too difficult to write down all the possible batting orders, wouldn't it? And then just count them. And that's sort of a common theme here, that as you get into counting problems that are complicated, you need to do the arithmetic, use these formulas rather than just count the number of possibilities. Keep in mind that permutations have an order associated with them. In that batting order, it's different, the guy that bats first and the person that bats second. So now we're going to turn to a different topic, the second major topic today, called combinations. And the main difference is that combinations don't have an order attached to them. It's like forming a committee. If I form a committee of 7 people, out of, say, 55 people, there's no order in that committee. It's not like I have to line them up in an order. They're just in a bundle here, the 7 people in the committee. So that's sort of the main difference. Let's do a very simple example with committees. Suppose you have a small club, and the club has 4 members: Alex, Bruce, Carly, and Dana. We'll call them A, B, C, D. And these 4 members want to form a subcommittee of 2 members. That subcommittee is going to do some special work. How many subcommittees, how many possible little 2-person committees are possible here using these 4 people? Well, we can enumerate them in this example, can't we? We could have Alex and Bruce in a committee, or Alex and Carly, or Alex and Dana. We could write those as AB, AC, and AD. And then we could have Bruce and Carly, and Bruce and Dana, and then we could have Carly and Dana. Now, I claim that's all the possible committees, because look, the committee of Alex and Bruce is the same as Bruce and Alex. There's no order here. We aren't doing a permutation. We're doing what are called combinations, so that committee's the same. We don't have to have Alex first and Bruce second. So there are really only 6 committees possible out of these 4 people. And here's the general theorem. These are called combinations of n elements taken r at a time, different from permutations of n objects taken r at a time. These are combinations. Order is not important. There's a symbol for this, NCR, capital C, and you have the subscripts n and r on either side. So it kind of looks like the other symbol. The formula here looks sort of like the permutation formula, but there's an added person in the denominator. It's now n factorial, all divided by n minus r factorial times r factorial. There's an extra r factorial in the denominator. Let's check our formula on that previous example. I think this is always an important idea in mathematics. When I learn mathematics and somebody gives me a formula, somebody gives me a theorem, I like to check it right away on some simple examples. That's not a proof that it's correct, but it gives me a lot of confidence in how to use it, and I think, well, it probably is true because it checked out here. And trust me, this is a true theorem. So, we had in that previous example 4 people, and we picked a committee of 2. So we were taking n elements, taken r at a time, 4 elements taken 2 at a time. So it would be 4C2 in our symbols, and the formula says that's 4 factorial divided by 4 minus 2 factorial, n minus r factorial, times r factorial, times 2 factorial. Let's simplify the numbers. 4 factorial divided by 2 factorial times 2 factorial, 24 divided by 4 equals 6, which is the answer we had before. Great, okay. Are you a fan of poker on television, Texas Hold'em? I'm always amazed on those shows that they can compute the probabilities of somebody winning in a certain situation. Let's do an elementary computation with poker, and you'll sort of get a feel for perhaps how they do that on television. So here's my fairly straightforward question. Remember that in a standard poker hand, there are 5 cards. You're dealt 5 cards, and the deck has 52 cards. So you're dealt 5 cards out of 52. Here's the question. How many different poker hands are possible? How many different poker hands are possible out of 52 cards dealing 5? Well, remember, a poker hand doesn't have any order attached to it. It doesn't matter how you arrange the cards in your hand. So this is a combination question. And the formula says n factorial over n minus r factorial times r factorial. Well, who's n and who's r? Well, we have 52 elements. So n is 52, and we're taking them 5 at a time, so r is 5. Plug in the numbers. Here we go. The numerator, 52 factorial. The denominator, 52 minus 5 factorial times r factorial times 5 factorial. Don't forget that 5 factorial down there. All right. That's a pretty ugly looking quotient, but let's do our trick. It works pretty well here. What are we going to do? Well, 52 minus 5 in the denominator is 47. So we have a 47 factorial down there. In the numerator, we have 52 factorial. Let's write that numerator as 52, 51, 50, 49, 48, 47 factorial. Stop there, 47 factorial. Cancel the 47 factorials, and we're left with 52 times 51 times 50 times 49 times 48 over 5 factorial. 5 factorial is 120. Now I do have to use a calculator, but it's not so bad here. And it turns out to be 2,598,960. So there are about 2.5 million possible poker hands. Kind of an interesting answer, I thought. It's actually not that many. And of course, some of these hands are winners. Like if you get dealt ace, king, queen, jack, 10 of spades. That's one of those 2.5 million hands, right? All right, so now if you watch poker on television, you'll have a better feel for perhaps how they're calculating some of those probabilities. Keep in mind with these permutations and combinations, the big difference is that combinations don't have an order attached to them, whereas permutations do. And again, that good news, not only are permutations built into calculators, but so are combinations. Both those formulas are in your calculator. Okay, on to lotteries. Florida has a lottery now. Most states have lotteries. Here is a typical example of a lottery game. So let me pose it this way. Suppose you have a lotto game in which a player chooses 6 distinct numbers from 1 to 49. Okay, so you're allowed to pick 6 numbers. They have to be different, and the numbers come from 1 to 49. How many different ways can you select these 6 numbers? How many ways can you select them? Okay, I think you see that this is going to be a combination problem because in this lotto game, it doesn't matter which number's first and which is second, etc. All you have to do is match the 6 numbers. So you pick 6 numbers. All right, so this is going to be 49 elements taken 6 at a time. So our formula is 49 factorial divided by 49 minus 6 factorial times 6 factorial. And I think you know now the tricks for simplifying that. Trust me, here's what you get. 13,983,816. Let's call it about 14 million. So there are about 14 million possible tickets that you could form with 6 digits, with 6 numbers. So what if the payoff for the lottery is $5 million? Wow, not a very good deal, is it? Here's another thing you could say. People have talked about this. Suppose you bought every lottery ticket, every possible combination. Well, then you would surely win, wouldn't you? But if they're $1 each, you're talking spending around $14 million to buy each lottery ticket. And sure, you might win that $5 million prize, but it might be even worse. You might have to share the prize with somebody else who also bought a winning ticket. So it's interesting to calculate these odds of these probabilities. I won't say probabilities yet, but these number of possibilities, number of lottery tickets possible, and then keep in mind what the payoff might be. Okay. We've spent today's lecture, this lecture on counting principles, permutations, combinations, and we did a little bit with factorials again and played around with some very practical problems, poker hands and lottery tickets and things like that. Next time we'll take these ideas and move to the field of probability. And we'll use these counting principles to develop odds. What's the probability of, say, winning the lottery? Or what's the probability of rolling a 7 with 2 dice? Those are the kinds of questions we'll look at next time when we move to probability. Thank you very much.